All right, what was the last thing? Oh yeah, this was me just saying that we could have saved data to any particular memory address, which could have then caused problems if we saved data to like an address of some instruction that is yet to run, and that can create some trouble, which of course would be very bad. All right, so let's make another program, a counting program. This is going to be another simple little program that we're going to write machine code. And when I say machine code, I mean like the zeros and ones, or of course the hex, same difference, right? Let's make a program that would do this. I just want it to print 0, 1, 2, 3, 4, 5, 6, forever. Now, of course, we know, based on our system, what could our system actually count to? 255, right? 255. But what would happen after hitting 255? 0, 1, 2, 3, 4. So it'll keep going. We know it'll keep going by virtue of just its design. But, you know, I want to make this program. This program will run forever. There'll be no halt, right? I mean, even in Python, this program doesn't end, right? It just goes. It'll count forever, and that's fine. So I want to make this program. So how do I do that? Well, in Python, it would look something like that. Count 0 while true, you know, like loop always. Print out the count, add 1 to the count. So what would the instructions need to be for machine code? Load 0 into register A, load 1 into register B. Now, in order to output something, we have to save the value from register A. Okay, so save the value, output the saved value, perform the addition, jump to instruction 3. Repeat, 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 forever. That's it. That's the program. Now, in this particular example, because 0 and 1 are small enough, I could use those other load instructions that we have. I don't need to say load from RAM. I could, but I could use the load D. Load A D and load B D. Load A direct, load B direct. I could do that. And it saves RAM addresses, right? Because if I needed to load from RAM, I need to have 0 and 1 saved somewhere. I mean, we could get fancy and generate these things programmatically. Okay, all our RAM addresses that are empty are 0 anyway, so we're not really losing anything. And then we can generate a 1 by adding 1. But now we're just working hard. Anyways, load 0 directly, load 1 directly, save, output, do addition, jump. Save, output, do addition, jump. Save, output, do addition, jump. There we go. Now, you even compare this to like the Python code. It's not even that far off, right? Okay, 0, the 1, print are these 2 steps. And you know, while true is up here, but you know, I guess the jump is at the bottom. But we could actually see in this particular example how related they are. So that's kind of nice. The current value of A is displayed by first saving it to RAM, then outputting it as an unsigned integer. If we did say output as a signed integer, what would this count to? But then what? Then go to negative 128. I mean, well, you know what? We'll do that in a second just to see how ridiculous it looks. But yeah. Addition adds the value in B, 1 to the current value stored in A, so like A plus equals B, or more specifically, A plus equals 1, since B is always 1. That's kind of how I'm doing it. And then finally, the program must loop, so a jump instruction is used to go to the address saving the value to A. And remember, saving the value to A is like the first step to output. So the complete machine code would look something like this. 2 was load direct. What value? 0. 4 is load direct into B. 1. 5F, that is save to memory address F. Save A to F. Output unsigned. And if you're like, how does he know that? It's because I remember them, okay? And who here's remembered them? Who here has memorized all the instructions? Some of them, maybe? Yeah, well. Anyways, that's save. And the reason I know is I'm like, okay, well, 0 is halt, 1 is load RAM, so this is, and then 3 is load B from RAM, 4 must be direct. And then 5 and 6 are the saves. Okay? 7 is add, I just know that. And then the outputs, you're like, D, how do you remember? Well, I remember F is halt, and E was print signed, and then D would therefore be. Anyways, I've memorized it just honestly, like I've memorized it by like their physical layout in order. Whatever. There is some memory work involved, nevertheless. Okay. So save, output, add, and then 9, jump to where? Address 2, 0, 1, 2. That's the save, output, add, save, output, add, save, output, add. And this will never end. It'll run forever. Again, we've saved here to address F. And you might go down here and be like, well, there's no F in there. There's nothing there. I know, because we don't need to load any data from the get-go. There's no program data here. It'll get calculated, the sum will be calculated programmatically and saved within the program. It's a runtime thing. All right, notice that the program has no halt, right? So what happens, we already talked about this, right? If we get to 255, so 8 ones, we add 1, we get the carry bit. The carry bit just kind of disappears. It gets lost into oblivion, and we restart with the 8 bits we have, which is back to 0. Yeah. Since the program never halts, it could run forever. We won't let it. It would run until it's turned off by something external to the system, though, which is kind of like an interesting thing to note, I suppose, is it will run forever, but unless something external from the system messes with it, it'll run forever. The number of clock cycles this will take is infinite. So now we're thinking like, okay, what's the resource cost of this? Well, the number of clock cycles, forever. It's never going to end. It'll run forever. The amount of RAM, pretty simple, right? 6. 1, 2, 3, 4, 5, 6, plus the F that we use at runtime. So one address used to store the data. Cool? Any questions about that program? Fairly straightforward. So let's go. And by the way, pay attention to how we're doing this, because you're going to have to do it in the assignment, right? If we want to load a program into RAM, we have to go File, Circuit-Specific Settings, Advanced. This must be checked, and then here we go and we navigate to the one we want. Fortunately, I'm already there, so I want add, subtract output. What do I want? I want counting. Open. Okay? Let's turn that off. I hit run. That's the program. Yeah, it's there. We're good. So now let's do it by hand. By the way, we were talking about this in lab. So like I can go here and click clock all I want, but if you just press C, it'll do it. And I can hold C, which is kind of nice, right? Should I stand here until it gets to 255? Yeah, you think so? No. How many clock cycles will this take like per cycle though? Let's think. 1, 2, 3, 4, 5, 6, 7, 8. Well, these two actually only happen first, right? Like getting A and B set up. Then, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5. So 16 clock cycles per like cycle, except the first one will require 20 because 1, 2, 3, 4, 5, oh no, 24, pardon me. We'll start a real-time clock. I don't know, let's do 50 hertz. No, that'd be only like 1 a second. Let's do 40, 80, 120. 240. There. All right, there we go. Now we're counting. Here we go. This time I will let it go to 255 because why not? It's always fun. Make sure we're not crazy. Imagine it didn't. Ooh, we'd be in big trouble. And yeah, there we go. Okay, we're good to go. Awesome. And then for the fun of it, let's stop. Now, actually, can I? No. Okay. How do I want to do this? Let's go desktop. What I'm going to do right now is I'm going to modify it to not do the unsigned printing. Let's do the signed, just for fun. Topics. Where are we? Programming? Counting. Is this right? No. Is it under control logic? Counting output, yes. Okay. All right. D, let's make this E. Save. Okay, now, did it actually change it? It did. Okay, good. So we should see it get to 127, and then, yeah, there we go. Cool. And it goes to -1, back to 0. So we'll go -1 to 0. So I guess if we could have started this at, so like if you look at it now, nothing looks wrong, right? It goes from -128 to, look, it'll go to 0 and it counts up. So now we've just kind of shifted, except of course it was weird because we started at 0. We went 0 to 127 and then -128 back to 0. Right? So it's like we started in the middle. But like, if we didn't know where we started, we would look at this and be like, oh, it's still counting like forever. It's not from 0 to whatever. It's starting, like it's going from this is the smallest number. But wouldn't it be nice to start at the smallest number? Yeah, okay, so let's modify our program to do that. So I want to start from -127. Or no, -128. What is -128 in binary? You calculating it? Come on, that's easy. 1, 0, 0, 0, 0, 0, 0, right? That's -128. Right? Let me put it this way. -1 is all ones. So the other end of that, but you know, knowing the sign, there we go, cool. So we need to put this into A. But I can't use load A direct, right? I can't put -128 in there. In fact, I can't put any 8 negative numbers into A with the direct load. Remember we talked about this? Who remembers why? Pardon?
It's too long.
Yeah, that's related. We'll review it in a moment, just because I think it's kind of important and fun to talk about. Let's go modify this program. So I want to start with so I want to actually load like 1E. You know, I don't like that. I'm gonna make this F, and then we'll make these E's. So now we're gonna save the data that we're calculating to here, the second last memory address. But I'm gonna load, so that would be like 8, 0. That would be, no, yeah. That would be 1, 2, 4. I missed a 0 there, by the way. 1, 2, 4, 8. Yeah. Because this is 8, 0. Right? Yeah? Yeah. Okay. So is it clear what I just did? I modified the program to load from memory address F, that number, into A. We can still load 1 into B, but now we're also not saving to F anymore, we're saving to E, and we're also outputting the signed. Yeah? Happy? Let's save this and rerun. So now we should start at -128. Looks good. Cool. Great. What if I wanted to count by 2s? Well, that's pretty easy. Just go here, and instead of adding a 1, let's make it an odd number. Odd numbers are more fun. Let's count by threes. I know we just counted by an odd number, but let's count by threes. Okay? Yeah, looks like it. I mean, we're going pretty fast, but I assume it's counting by threes because that's what the program says. Right? Pretty cool. Oh, what if I want to count backwards? Okay, well, that's not too bad. I can just say, instead of adding, let's subtract. Right? I guess I could add -1, but again, I can't put a negative number with load direct. So let's just do subtraction. Now we start at -128, but then immediately go to positive 127, which is kind of strange, but to fix that, maybe we start at a, I keep losing track of where I'm hiding it here. There. So I guess instead of starting here, we could start at like 7F. That would be 0, 1, 1, 1, 1, 1, 1, 1, right? Oh wait, but is that? Yeah, that should be it. Yeah. There, yeah, that looks fine. Yeah, there we go. Cool. I don't know. It's kind of fun. Simple little program. But again, the system is running it on itself. This is a pretty big deal. Now, just as a reminder, the reason why we can't load direct a negative number is because the output from the instruction register can only be 4 bits wide, right? So if I was like, oh, I want to output the number -4. What is -4 in 4 bits? 1, 1, 1, 1. Okay? Problem is, I put that on the bus immediately adds 0, 0, 0, 0 to the front of it. That is not -4, not -1, that's 15. -1 with 8 bits is 1, 1, 1, 1, 1, 1, 1, 1. We've got these extra 4 ones that we would have needed. And we can't actually pad it with ones unless we really went on to add like some extra hardware to the system, which, look, we always have a trade-off. Add more hardware to add this feature. Do we really care? I can still add negative numbers. Is it worth the pain and suffering of figuring out the hardware and the logic for that? Maybe, maybe. Not to me right now, that's for sure. But maybe in your case it really does matter, fine. But, it's always that trade-off, right? So any questions about any of this? No, everyone's happy? All right. Let's go back. I'm just going to go back and undo all those changes. There. Cool. Now, we can program the system. And obviously, we have a giant limitation in that we only have really the biggest limitation is that it's an 8-bit wide bus. We only have 16 memory addresses. It's 16 bytes. That's really not a lot, okay? So that is a significant limitation. But it has another limitation. Another limitation that's not really a consequence of the size of the bus. I could make this, I'm willing to bet if on the last assignment, I'm not going to say this, but if on the last assignment I say, take our design and make it 16, instead of 8 bits wide, make it 16 bits wide, you could do it. It'd be kind of tedious, but you could do it, right? And if you were to do that, yeah, we would have a lot more RAM. What's 2 to the power of 16, right? Well, that's a lot more. So even if we were to do that, this system would have a huge limitation. And the limitation is we can't make a decision. Our program cannot make a decision. And without the ability to make a decision, we aren't going to be Turing complete. We're not going to have a system, like it can't play Doom in that case, okay? If it could make a decision, it could play Doom if it had enough RAM. So, and for those of you that don't, raise your hand if you don't know why I say it could play Doom. Okay, here's why. It's a bit of a joke where, like, can I make this computer, whatever it is, play the game Doom from like 1990 whatever, right? And so people have like implemented Doom in like Minecraft, for example, okay? So it's turned into like a bit of a joke. And it's so much so that it's like a benchmark almost for like, is it Turing complete? You can demonstrate it's a fully capable computer if you can make it play Doom. So maybe one day I'll have a version of this course where it can play Doom. But right now, with 16 bytes of RAM, we're in trouble. All right, anyways, so that's why it's a bit of a joke, but it kind of makes the point that if it can play Doom, it's a computer. And most people would be satisfied to be like, yeah, it's a computer. If you Google, like, can it play Doom, I'm sure you will find countless jokes about it online. All right, it can't make a decision. So, like, if I were to say, given some number, output 1 if it's less than 0, or pardon me, output 1 if it's less than 10, otherwise 0. Okay? Like, if number less than 10 is effectively what I want to be able to do here. I want to be able to have like if statements. Obviously, we're programming in machine code. We can't write if, but I want, bless you, I want the ability to do the same thing. I want the ability to branch. We can't do that right now. Our system does not have that ability. So, we're going to make it have that ability because that's really the big thing that's missing right now. I can't branch. So, okay, let's consider for a moment, before we start thinking, how do I make our system do that? Let's consider for a moment, like how close can we get to this with our system, okay? So let's say I want to check if a value is less than 10. Well, no, we've kind of played with this idea, by the way, in lab, right? But like, if a value is less than 10, how would I do that? Well, okay, let's load the value into register A. And I want to know, is it less than 10? So I could check the difference, right? I could be like, this number minus 10. If a number minus 10 is less than 0, what does that mean? It means it's less than 10, exactly. Okay, so we know, like, okay, you know, we can do subtraction. Okay, so that's good. And if I want to know, like, okay, is the number less than or equal to 10? Okay, well, I could check if it's 0 or less than 0, I guess, right? Right? And if the number is not that, like, let's say the number is not negative, then it must be greater than 10. Let me put it this way. 5 minus 10, right? We know 5 is less than 10. What's 5 minus 10? Negative 5. 9 minus 10. What's 9 minus 10? Negative 1. And I know 9 is in fact less than 10. 10 minus 10? Well, that's 0. And then like 11 minus 10? Well, that's 1. And clearly 11 is greater than 10. 10 is not less than 10. 15 minus 10? Well, that's 5. Okay, clearly only for the negative numbers. I don't know, can you see that here? Well, only for the results that are negative are when these values are actually less than 10. Do you agree? Okay, that's like what we're getting at here. All right, so what is the general idea of what a program would look like in our system to make this happen? Okay, so load the value into register A. If the value in A is less than 10, I want to output 1 and then halt. Otherwise, output 0 and then halt. That's what I would like want my program to look like, right? Load a value. Is it less than 10? We magically find out. Output 1, halt. Otherwise, output 0, halt. That's the functionality we want, but we don't have that functionality yet, do we? So there is no way for our system to do this. But we do have, like, we kind of do have a way to branch though, right? When I say branch, maybe branch isn't the right word. We have a way, like, okay, what would branch mean in our RAM? Imagine this was in RAM. Like, okay, maybe this isn't like address 0. Address 1, address 2, address 3, address 4, address 5, address 6. If this case was not true, I don't want the program counter to go to like 3, do I? Or 0, 1, 2, pardon me. I don't want it to go to 2. I want the program counter to not do this next. I want it to go like do this next. So we have to like jump around RAM. And we already have an ability to jump, right? We've got the jump operation. But the jump operation doesn't branch though. Like it jumps around RAM, but like it always does that. It doesn't have an ability to make a decision. It's always going to do that jumping. But is there a way we can make it do the jump under certain conditions? That's what we want to do. Because if I could say, if this is not true, jump here, right? Like I could do that. Or I could invert these and be like, if it is true, jump here, otherwise, whatever. It doesn't matter the order that we do these things. But if some condition's true, then we want to jump. Then we would have a branch. Basically, go to, like, run, like, in this case, it would say, go to address 2 to run next, or address 2, 3, 4 to run next. Okay? That's like what I would say. Assuming this would be like 0, 1, 2, 3, 4, 5. This otherwise wouldn't really be in RAM, I guess, but yeah. Do I have? Yeah. However, the current instruction does provide a way. Therefore, using the idea of a jump, the program can be reframed. So load value into register A. If register A's value is less than 10, jump to a part of RAM containing the following instruction. Otherwise, do that. That's like how we're reframing it, okay? It's the same thing, I just, So here's like what we could have here, right? Now here, I've got my machine code, but I've also got parentheses describing what's going on, kind of like comments. Now, if you put this into digital, it's not going to work. It's going to be like, I can't parse all that crap. Yeah, it's fine. I'm doing this here for the sake of demonstration. So the first thing is load data from address F into A. What's an address F? Some data to check. I don't know what it is. Obviously, at runtime, I enter or before runtime, I put a number in here, a specific number to run. But this is what I want to check. Okay? So I load that into A. Then something, jump to address 4 if less than 10. So 0, 1, 2, 3, 4. DE, that's output this one, that's a 1. So this is like what I output if it's not less than 10. And this is what I output if it is less than 10. Okay? So these are just like data for outputting. So if it is less than 4, I'm going to jump somehow magically to here and then halt. If it's not, I'm not going to jump, output this value, the 0, halt. Do we see? Now you might say, you've got 2 halts here. Should you only have 1 halt and then you can do another jump? Fine, it doesn't matter, right? I'll show you what I mean here. I'll show you what I mean now, because I think it's kind of nice and fun to think about how these programs can change, especially for such simple things. What is happening? I did no such thing. So There are people out there that would say like your program can like halt in 2 different areas, and that's not good. Those people they're not right, but they're not wrong. There's something to be said about having like a 1 exit location for your code. So what you could do in a situation like that is say like, what was jump always? 9, and then 0, 1, 2, 3, 4, 5. Yeah. So if you're one of those people that's like, I don't like having 2 halts, fine, do that. You're not saving any RAM. We still need to jump to there, but you know, if you're one of those people, there you go. I've satisfied you. Are you one of those people? Maybe, sometimes. To be clear about what I mean is, before I had 2 halts, basically the program, like something, we branch, and then halt. I'll do like H for halt. That's like the flow, right? There are people out there that would be like, you shouldn't have 2 places where it could end. So all I'm doing is, shoot, where's my eraser? Effectively, I'm having it like come back with that jump. Okay? Is it clear what I mean? Yeah, okay. All right, cool. What's Notepad? Yeah, okay, cool. All right, great. So problem solved. I mean, logically, we know what we would want, but our system can't do that. It's great and all to think of an instruction that can do that, but if I were to say to you, okay, go make that instruction, our system doesn't have that ability. We don't have the hardware to do that. Think about it, right? How can we make it jump? You look at the hardware, it's just, there's nothing there. I can make this an exercise and you'll lose your minds because there's nothing there to do it. We're missing a key feature here. So it's great to have, like, this is what we want to be able to do. Can we do it? No, not yet. All we have to do is add a little bit more hardware to our system, and then we can do it. Now, I'll warn you. It's not trivial. It's not overly complex, I want to be clear, but it's definitely not trivial. Okay? Any questions about the logic that we want to have? And is it clear what I mean by the logic? Like, if we had the ability to jump, if I had a magic instruction that would be like jump if, then we could do this. We just need that like jump if. What would that even mean? How can we do it? Now, of course, if you've been doing the labs or the 3rd assignment, you already kind of know, okay, we have an ability to check conditions. So like, there's clearly something there. Yeah. Now, we're not going to do it with a comparator. We're going to keep it simple. So unfortunately, the jump instruction available always jumps. There's no condition, like I was saying. Therefore, like, what are we going to do? We have room. We have 3 unused instructions, right? We had 16 possible. We only used 13. So we have room. We could add more instructions. But again, having the room to add the instruction is not the problem. The problem is the hardware doesn't exist to do this. So what should the conditions be? How should the system handle it? Okay. So we want to be able to do a jump on a condition. Now, by the way, I think I probably do mention this as we go. Technically, okay, what should the conditions be? How many different conditions can we check? Is it greater than, less than, equal to, all these different things, right? There's a lot of things we could check. Now, technically speaking, all you really need is the ability to check one condition. Not a special condition, just a condition, and then suddenly you have a Turing-complete computer. Now, just because it is doesn't mean it's easy to use. So we're going to add a variety of different conditions that we can check that make it easier to program for. But technically speaking, to make a Turing-complete computer, all we need is the ability to check like a condition, and then we're good to go. All right, anyways. So having a, like, what should a condition be? Should I make an instruction that says, hey, are you less than 10? No, that's stupid, right? That'd be like writing that's stupid. It's too specific. It might be very helpful in one very special case when you need to check if a value is less than 10. No, you want to know, is a value less than some arbitrary value or something, right? So what we'll do, because we just talked about it, we just said like, okay, if I can check if something is less than 0, or if I can check if something is 0, first of all, if I can check if something is 0, I can check if two numbers are equal, right? Why? If the difference between the two numbers is 0, they're equal, right? If a number is less than 10, or less than 10, if a number is less than 0, if it's negative, well, if the difference is negative, that means something, that tells us something, right? So we're not going to say, hey, is something less than 10? No. We could say like, okay, is it less than 0? And we're also going to want another condition to check if it is 0. And with these two conditions, we've got a lot of power now. Technically, we only need one, but it's going to be nicer to have both. With that, yeah, like here's what I was saying. Okay, value minus 10 is less than 0, then value is less than 10, right? It's inequalities. Move things around. There you go. And the equals is nice. So yeah, okay, here's what I say. I'll read it out because I want to make sure I don't miss something critical here. Technically, the system only needs the ability to check one condition to be functionally complete. For example, only having the ability to check if the value is 0 would be enough for a system like this to compute anything computable. Now, what is computable? It's vague. However, consider the number of steps required to check if a number is less than 10, with only the ability to check if some value is 0 versus the ability to check more conditions like less than 0. Okay? Only with 0, what I could do is be like, okay, if I want to know if a number is less than 10, and I have the ability to check if a number is less than 0, how do I check it? Number minus 10, is it less than 0 or not? Okay? If I only have the ability to check equals, I'm kind of in trouble. What would that look like? I can still do it, but my program has to get a lot bigger because I don't have a specific instruction to check for me. What I would do is I would keep subtracting 1 and then check if the number is less than, if it is 0, like if I ever hit 0, right? Do you see my point? So there would be a lot more. And in fact, with more instructions, let me put it this way. If the numbers are bigger, look, subtraction is subtraction, right? With the adder, how many clock cycles does it take to add two numbers together? Don't even think of our system. If you have an adder, how many clock cycles? 0. It's a non-sequential circuit. You put two numbers in, it gives you the output. Same with subtraction, right? So what's the computational complexity of the two numbers? It's a constant time thing to check if something, right? But if I had to like loop and keep checking, do I ever hit 0 while decrementing? I fear I'm being unclear, and I am conscious of time. If I say x minus 10, okay, if that is less than 0, that means x is less than 10, right? I can do this calculation like that, okay? Cool. And then I guess I do the comparison, which happens in one step. I guess somehow, we don't know what the comparison really looks like yet, but whatever. If I had to say, okay, is x less than 10? Okay, I need to loop 10 times, okay? And I'm going to subtract 1 every time and check if it's less than 0, or if it is 0, okay? If I ever hit 0 before I'm done looping 10 times, then it must ultimately become less than 0, meaning it is less than, right? Cool. But of course, how many times does this have to run? Well, potentially 10 times, So this is, not only do I have to do it programmatically, it also takes longer. There's like computational complexity involved. Oof. So hopefully this is a clear example of how your decision of what instructions you have can really affect what your programs look like and how good they are. Do you see? Like it's really, there's so many different dimensions on how to optimize your system. It's not just about optimizing code, it's about optimizing what instructions there are, what your hardware is, and all of that stuff, which I think is pretty cool. All right, so therefore, to increase flexibility and ease of programming, several conditions will be included in our system. So we talked about 2. Another condition that we're going to have is an overflow one, okay? If the overflow bit, if the carry bit is ever high after doing an operation, we'll crash. If the carry bit's ever high, well, we'll halt. I don't know. We can stop. Or maybe we, I don't know, do something else. Start counting backwards, whatever. Okay? Fun? All right. So since since our system's 8 bits, overflows may be common. We might want to check if we have an overflow because that might mean something, right? So therefore, 3 conditions will be included. 0, to check if some value is less than 0. Although, really, this one's tricky because, like, how can we check if a number is less than 0? The sign bit, but it's not really a sign bit, but it kind of is a sign bit. And so if I give you this number, is that number less than 0?
Is there a sign bit?
You tell me.
Well, I mean, that could be anything, but yes.
1, 2, 3, 4, 5, 6, 7, 8. No, it's just 255.
Oh, see?
Right? So the problem is it an assigned or unsigned number? So really, we don't actually have the ability. You will see. I will show you. I will hopefully make clear that. So we're going to check if a number is 0. If some value is less than 0, kind of. And we'll check for if an overflow happened. Now, so like I was saying, though, if some value is less than 0, really all we can ever do is check the most significant bit, right? If the most significant bit is high, then we can make a decision. If we're dealing with numbers that might be negative, okay, great, now we know, now we're cooking, but otherwise, who knows what's going on. We just have to be careful. What does it mean? So checking an overflow is a little trickier, though, than the other conditions because, like, you can't just look at the number. Like, if I want to know if something is 0, I can look at it, right? If I want to know if that most significant bit is high, how do I just look at it. If I've given you a number and I say, like, hey, did an overflow happen? You're left going like, what? That has nothing to, I only have 8 bits. So we need a little bit more hardware or something to check that, but we'll see that shortly. Yeah, and so like an overflow could only have happened if it was the result of some arithmetic here, whether it was addition or subtraction, right? That's the only way an overflow could happen. If I give you the number 255 and say like, hey, was there an overflow? You're left going like, I don't know. So we would have to have known if some like operation caused it to happen, okay? Cool. You might remember this was the design of like, this is like the high level idea of an ALU. This is the common symbol you see. Operand, A, B, some result, and it's got some like opcode, right? Like if you remember, based on the ALUs you designed, if you give it different codes, maybe this ALU is going to do addition, subtraction, multiplication, a barrel shift, some operation, who cares? Maybe it's and, or, not, whatever. But I talked about these magical status things here, these side effects, these yucky things right here. That's what we're talking about right now. If this operation just caused a carry bit to go, that's a status symbol or signal. Okay? That's what's going on. I guess this ALU could also get status in as well. If the last thing we just did caused an overflow, maybe it affects how this works. It has the ability to affect itself. There's that weird pattern again that shows up in anything interesting. The ability for something to affect itself. So that's pretty neat. In fact, like, with this, like, okay, it should be clear, like, okay, if the last operation caused an overflow, that's a status signal. We could save that information. Yes, it did. So now what? We could also do the same thing with the 0 and negative, or sign significant bit. If the last operation resulted in a 0, that could be another status signal. And we could remember that. Or maybe if the significant bit was high, I'll remember that. Then if that signal's high, if I have a jump, I can be like, okay, if this signal is high, that jump will do one thing or not. That's where we're going. If you go and look at the importable ALU in digital, which by the way is not under the components thing, you'd have to like import it another way. But if you go and you look at the ALU, this like you could get this in digital, and if you do, you will see A, B, this is a carry in, opcode, which am I doing add, and, subtract, multiply, whatever. Y is the output, 0, negative, carry. It's got 3 status signals that it keeps track of. That's what we're going to be working towards. It's now just a matter of hardware to be able to keep track of those signals. And then if those signals are high, my instructions have to work a little differently. Any questions about that? All right, we'll end here for today.